Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Welcome to lecture number 12 on very important vacuum pump known as steam jet ejector. As a part of production of vacuum, it is also a medium vacuum pump. It can be a replacement to rotary pump whenever your requirement is very high. That means the pumping speeds enormously. That means value of pumping speed is roughly like 30,000 meter cube, 40,000 meter cube. You cannot imagine such things with rotary pump. Rotary pump is 5 meter cube, 10 meter cube, 20 meter cube, 100 meter cube maximum. But when you want to go to 30,000 meter cube per hour, this is the only pump. So industrially it is very important. Where for high-tech industries like electronic industry, space technology, space simulation chambers, you may not be using these pumps for obvious reason, because ultra-high vacuum technology will not tolerate any water vapor during its history of evacuation from the atmosphere. So, even though these pumps have got enormous pumping speed, they are limited to only process applications like pharmaceutical, chemical, food processing, steel degassing little bit, and little bit of paper industries, or wherever huge amount of water vapor has to be removed from any particular application. We shall see what are those applications later. As the name suggests, steam jet ejector is formed out of a jet utilizing steam. So, wherever in an industry you have waste steam available, this is ideal pump, because that waste steam can be used to produce vacuum. You do not require any extra electrical energy to run vacuum pump. And steam is also basically water vapor, high temperature. So, you can again condense it using suitable condensers and again recirculate it or utilize it after some treatment, etc. So, it is a friendly technology. Since we are dealing with high pressure steam, regular what you call precautions that we take with high pressures and steam handling, which is nothing. In power plants and all, we regularly do it, steam handling. Even in train technology, etc., steam handling has become very popular, and it is well established technology. And controlling steam flow rate and associated dangers, handling the steam equipment, steam chest, high pressure, these are all well established. So, it is a typical well established technology, otherwise is being used particularly in an industry when there is a waste steam availability to produce the vacuum requirements of that particular application. That application can be a drying application, it can be a distillation application in a pharmaceutical or chemical industries, it can be a steel degassing application or a paper drying applications. So, we will be introducing the steam jet ejector. Later, we will see the constructional aspects of steam jet ejector, what are the main building blocks. After that, we will see the working principle of a typical steam jet ejector. At the end, we will also give you an idea of typical applications for which steam jet ejector is extremely attractive compared to other pumps, or steam jet ejector is the only option type of thing. But of course, there are some contenders in the last 15-20 years like dry technologies like screw pumps and claw pumps. These are coming nowadays, and they are slowly replacing steam jet ejectors and water ring pumps in certain applications where very huge pumping speeds are not required, like thousands of meter cube, that is out, but hundreds of meter cube type of steam jet ejectors can be easily replaced by a roots blower boosted screw pumps, for example, or a claw pumps. This type of combinations are much better compared to even steam jet ejector in certain applications where the technology is dry. You cannot have any water vapors. That type of limitations are there in the process. Then these technologies are coming up in chemical and certain pharmaceutical industries. But in very large scale applications, steam jet ejector is the only pump which can pump huge volumes at a very high rapid rate. Let us see how it looks like. You can see the figure here, the one that is there, steam jet ejector. It is the first stage of a typical jet ejector that is used in steel degassing plant, and you can look at the size of it. It is of the order of building size. And right side, little medium scale, multiple steam jet ejectors are connected in series with intercondensers in between for various pharmaceutical and chemical applications. Okay. These are taken from a very good book. I suggest to all chemical and pharmaceutical sectors to read this book, Vacuum Technology in Chemical Industry by Wolfgang Jurich. There are good books in vacuum technology like Roth and Heblanian and other things. Of course, I have also written a book on vacuum science and technology from Allied Publishers. But these are very specialized books where chemical applications, pharmaceutical applications are highlighted, and that is where steam jet ejectors, water ring pumps with boosters, and nowadays dry pumps like screw pumps and claw pumps. I am just giving you some picture of an industrial scenario, but we will focus today right now only on steam jet ejector, its working principles. But those people who are going to start startups in various applications, they should also know its competitors and what is to be used when. There are 2-3 things in vacuum technology: operating pressure. At that operating pressure, what is the load it can handle? You can get very high vacuum using a small rotary pump, but it cannot handle more than 1 meter cube per hour. Then it may be good for certain industries like X-ray tube evacuation, etc. A small pipe, but it is a high-tech application. Okay, you can use that. But when you are employing a pump to evacuate huge loading of 30,000 meter cube per hour type of thing, of continuously sucking such exhaust gases or fumes coming from exhaust management in industry, such applications you cannot obviously use a rotary pump. That is with respect to loading. And rotary pumps and other pumps require electrical things. Here it requires only steam. And if that steam is available in a byproduct or a waste product or something, you can definitely get a lot of advantages. So, they provide the best way to produce low or medium vacuum in process plants because of ease of construction. Though little bit of high pressure and steam are there, but these are well proven. All the mechanical engineers are fully confident to handle steam and high pressure, and these are not very ultra high pressures. These are all 10 atmospheres, medium pressures, maximum 20 atmospheres. A typical cylinder contains 200 atmospheres pressure, 3000 psi. Okay. So, these are all 20 atmospheres type, medium pressure, and they can be easily maintained. Their capacities can be varied from very small volumes to enormous quantities like 30,000 meter cube per hour. They can be connected in series and parallel combinations to produce various suction speeds as well as various vacuum levels. And there are no moving parts in this pump like rotary vane pump or piston pump or anything, because the fluid itself is moving. Jet it is basically, it is a liquid type of thing. It is not liquid, it is a steam, high dense steam, okay, and quite cheap, and readily available fluids like waste steam can be nicely exploited to get a fairly good amount of vacuum pump, vacuum level and high capacity suction. So, industrial atmosphere, these are heavily being used nowadays. You enter into any chemical industry or pharmaceutical industries or paper industry or any such thing, you will find lot of these steam jet ejectors, particularly since up to the first half of this 20th century, maybe up to 60, 70. Later, for few applications for high tech pharmaceutical etc., people are going for screw pumps because they are dry in nature, okay, and they are going for claw pumps etc. But when it comes to large volumes, this is the only alternative. Okay. Basically, they are positive displacement, but using momentum exchange pump. In a way, this positive displacement word is a very peculiar word. Okay. It displaces, but actually it lifts the gas, mixes them and sucks them and takes them out. In a way, they are displaced. Okay. It is not like a typical displacement like a rotor is moving, a volume of gas is taken and it is exhausted type thing. This is jet pumps they are carrying loads along with them, but later they are leaving them and the steam is again condensed back. In a way, the load is displaced in a way. There are very good animations available in net, you can see that, and a lot of manufacturers are manufacturing variety of steam jet ejectors of various capacities. And the control systems, valves, its pressure, temperature, all these things are well established now, and remotely you can control them also in industrial atmosphere. Okay. After that brief introduction, let us see the constructional aspect of it. It contains a small nozzle through which a high pressure steam or a motive fluid we call it, that gets a lot of sort of converging and then it diverges from here. So, this converging diverging creates this high pressure steam to be converted into high velocity steam. These converging diverging nozzles, sonic, supersonic, hypersonic, these are this is the heartline of all aeronautical engineers, to some extent mechanical engineers also. And what is supersonic, what is subsonic, I am not going into details of that, because it is a very involved subject. It is almost like 60% of the BTech aeronautical, they deal with variety of converging diverging nozzles and supersonic and subsonic flows etc. It is a very involved process. I will not go into that, but it basically works on momentum transfer of the molecules to be removed by the supersonic steam. Only when supersonic you will get certain effects which can produce good amount of vacuum technology. So, it consists of three parts. One is steam nozzle, then suction chamber, this is the suction chamber, this is the steam nozzle. Third thing, this extension, the entire thing can be called as diffuser. That is also basically a converging diverging type of structure, but it is more popularly known as a diffuser. Actually, it will convert the velocity head back into pressure head, and here the high pressure energy is converted into high velocity energy. And since we are having fairly high pressure like 5 to 6 atmospheric pressure through a nozzle, when it suddenly expands, it produces very high velocity, Mach number of 3 to 4, a typical high velocity of 1000 meters per second, which we call as supersonic velocity. This is a expansion process basically. And during that expansion process, such a high velocity forward moving jet produces a suction around that, because when high speed of air jet or any air jet or liquid jet or steam jet is suddenly going in forward direction, you get a suction effect. This we can see in our day to day lives also, when we spray something in house, that also basically similar principle. So, here we are using it in a very large scale. So, this high pressure, high temperature steam is suddenly expanded through this nozzle into this chamber, where velocity goes up to supersonic velocity, and this fluid is called motive fluid, and in the process of going with such high velocity into another section called diffuser, which itself looks like a converging diverging structure, you will get a suction effect here. That suction effect is quite huge, and you can utilize it for exhausting various gases or maintaining a good amount of vacuum in a very, very large chambers. This can be connected to a big steel, molten steel, having degassing huge amounts of gases, they have to be removed, so that you will get a good quality steel. Such applications, first of all, it is coming with little higher temperatures. Second is all sorts of vapors are coming in a huge quantity. This fellow can be, this flange can be connected to that chamber, and it will be able to handle all of them, and they will come here. This high pressure converted into supersonic stream, and the suction fluid, which is our process fluid, coming here, they both get mixed up here. So, that way this place can be called as a mixing chamber. And you will see this converging nozzle, those who are doing B.Tech, they know very well fluid mechanics, if they have some idea. In a supersonic set, supersonic streams in a flow, when area is decreasing, the velocity, what will happen? Normally, common sense says something else in a fluid, etc. When area is trying to decrease, velocity will be more, etc. So, whereas supersonic things, it is different. Okay. When area is suddenly decreasing in a supersonic velocity, the velocity starts coming down. Okay. So, high pressure motive steam initially, which is adiabatically expanding into this portion, having supersonic velocity, catches this suction fluid at a fairly good vacuum level and very high flow rate, and both of them get mixed up here, and velocity starts decreasing in this converging portion of the diffuser. And we will have to design this length in such a way that by the time it comes to the throat section, the mixture, which is mixture of suction fluid as well as the steam, high velocity steam together, that mixture velocity comes almost to the sonic speed. That is the throat section. So, once it slightly crosses the sonic speed, from supersonic to sonic, now we have to maintain an expanding type of area now. As area increases, now reverse effect, as area increases, velocity decreases. Here, as area decreases, velocity decreases, because it is supersonic, here it is subsonic. So, we have to manage the flow rates, suction, temperatures, all of them in such a way at this portion or mixing ratio, etc., I am not going to detail because of lack of time, because it is a huge amount of design is involved, lot of CFD is involved there. We have to see to that in the throat section you will start getting the almost like a sonic velocity, and we will see to that it is crossing that velocity, and afterwards the pressure head picks up. At such a way, at the outlet, if it is almost like atmospheric, then you can freely leave that. But along with that, the energy content of this hot steam, that is also wasted. So, we should not do that. Or with one stage you may not get good amount of suction. So, what we do? We connect this outlet to the inlet of another steam jet ejector. That means, this type of flange will be connected here. Starting load is your process application. It can be a steel degassing, or it can be a vacuum distillation, or a drying operation, or whatever industrial application. So, that is getting mixed up with this steam and goes here. Our idea is to throw away this. We need not throw away the steam, because water is scarce. We have to retain it. We cannot throw. So, that way it will be reused again. So, we need to keep between this exhaust of this and the inlet of the second stage a intercondenser. That intercondenser will condense this steam selectively, and the other portions like vapors and gases coming out from the load, they will continue to the second stage, third stage, like that. And if you connect more such stages in series, you will get better vacuum here. If you only single stage, it will be little poor vacuum. So, this is the principle of producing a suction, that means producing a vacuum under loading conditions of huge load. So, I repeat, a high pressure steam suddenly expands adiabatically in the motive nozzle, and it goes to the supersonic velocity, and in a converging portion the velocity, when it tries to decrease, since still it is supersonic, the velocity decreases with the area decreasing. During that time there will be suction effect here, huge suction. Whatever you wanted to remove in a process chamber, whether it is a tomato juice or sauce or something process applications like chemical or food processing, etc., all the vapors will come here. They will be mixed up. They will not have supersonic velocity. This supersonic steam will be getting mixed up here, momentum will be transferred, and that way the velocity will further come down, but anyway reducing area also facilitates that, and finally it comes to the throat area. Then onwards, since it has come to the sonic speed, then increasing area will also create velocity further decrease, and pressure head picks up. At the outlet it gets exhausted if it is single stage, otherwise it is connected with a intercooler to condense the steam back, which is a working fluid, and the load gases from the process, they will be conveyed to the next stage if it is a multi-stage. So, in the construction itself we could understand the operating principle here, because there is nothing much moving here. So, construction itself, the action and construction go hand in hand. So, this is what all I have told you. Here I am seeing this is the motive nozzle, this is the diffuser portion, and you see high pressure steam is coming. This is the pressure profile, this is the velocity profile of steam, and the velocity profile of the suction fluid. I have, for your sake, I am producing a structure like this, same thing, photograph of that. So, this is the suction fluid, yellow fluid, this is the steam, and it comes to high sonic, and both of them get mixed up and comes to sonic speed, and then goes to the pressure head. Okay. So, from high pressure it suddenly pressure comes down, velocity picks up like anything. In the diffuser portion it starts coming down, pressure picks up. These are corresponding lines in the assembly, and both when the suction fluid from this port gets mixed up with this supersonic steam, both of them together will further slow down till it comes to the throat portion, Once it crosses the sonic speed, then increasing area will create further reduction in the velocity of the combined mixture, and during that time pressure head further picks up, and this pressure head can be connected to a section of another thing with an intercooler, or it can be exhausted also. So, see, one stage will create 50 torr, 2 stages create 5 torr, 3 stages will create 2 torr, 4 stages 0.2 torr, 5 stages 0.3 torr, 6 stages 0.3. And typical materials that we will be using for steam jet ejector are stainless steel, bronze, gunmetal, cast iron, etc. for the various nozzles, because they have to withstand such high temperatures and jerk and high pressure, etc. Non-metals are also frequently used in highly corrosive applications like porcelain and graphite, etc. But we have to be careful in handling these things, and we have to maintain the pressure at the steam chest, and we have to see to that velocities are properly matching within the design length of the diffuser, so that they go to the throat portion automatically into sonic speed for a particular load. If load is different, then you will have to adjust the flow rate of the steam. So, there are a lot of valve controllers are there, but there is no physical motion of any piston or anything here. Okay. So, there are plus and minus of both these things, but nowadays very high quality process controllers are available to control the flow rates and all. Okay. So, typically an ejector discharging to atmosphere can be designed for a compression ratio of 20:1, but most of the time economics normally limits to 10:1. But single stage ejectors are not that popular. 2 stage, 3 stage ejectors are more popular. How they look like? See, first stage, second stage. That means the steam is coming here and the process fluid is coming here mixed up, but still the pressure may not be high enough, so that if you put a condenser at that temperature, it may not be condensing, because it has not reached the saturation point. There is no point in putting a condenser there. So, let it both together go to the second stage, and at the exhaust stage the steam partial pressure goes to the saturation point. At that time you can put an intercondenser. There are varieties of intercondensers, and the liquid, the steam will be condensed here, but vacuum goes on, and that separation is maintained by a barometric leg of 10 meters height, so that the water gets collected up to here, and excess water continuously goes out, and you can collect that water, etc. So, that way the remaining portion which is not condensed will go to the next stage, and again it goes to the intercondenser, third stage, fourth stage, like that. Several stages together can produce a good amount of vacuum. So, depending on the vacuum level, flow rate level, purity level, etc., or mass flow requirements of your process fluids, you will have to design different varieties of steam jets. If you want to eliminate too many steam jet ejectors, you can connect a watering pump as a backing of the steam jet ejector. So, combinations also exist, and in between you can also connect roots blowers, etc. Varieties of combinations are available with the watering pump and steam jet ejector and roots blowers, with different amounts of boosting or different amounts of backing, with intercondensers popularly, and economics finally decides, convenience finally decides. With the proper safety precautions, you can certainly use it for process applications where huge amount of suction is required. They are heavily used in process applications dealing with chemical, pharmaceutical, paper industry and steel degassing. These are 4 mega applications where very large quantities of things have to be removed. So, the engineer has to handle the heat exchangers here, intercondensers and high pressure steam and ejector principles, little bit of knowledge of supersonic, subsonic design of diffuser, etc., and then properly mixing the suction fluid with this, a little bit of chemistry and precautions that it should not be exposed to atmosphere. In case you make some mistake, suddenly there will be reverse flow, there will be shock waves coming there, and the entire thing will come to, instead of removing the fluid, if you look at the figure, instead of removing the suction here, the steam may come into the actual process. So, your actual process chamber may be flooded with steam. You should take care of all those things. If you can do that with a single stage, 2 stages and proper flow rate controllers, you can achieve very good flow rate with very high quality vacuum. And you can look at little bit of animation, the steam that is coming and suction fluid is catching immediately. So, this type of animations are available in literature. You can see varieties of animations, and principles are very well explained. You can use CFD also for modeling these things. Okay. So, what are the uses, advantages and limitations? I already told you. So, I will be repeating towards the end. This is the last slide. These are process industries involving exhausting fumes, exhausting air from condensers, vacuum evaporation of very large scale, distillations, crystallizations, refrigerations, used in, even there is a jet refrigeration nowadays, steam jet refrigerations. Once upon a time they were not attractive because other refrigerators are very popular, but now lots of environmental things, we are again going into a steam jet type of refrigerators, particularly for large scale refrigeration. Though you have to spend energy to create steam, etc., and all, you have to take care of that. Advantages are low investment costs compared to other pumps, and no water gas separation is required to be installed, no seal water cooler is required, that sealing fluid type of things are not there, only we require intercoolers to condense the steam, etc., and no moving parts. So, maintenance is very low, very compact construction, and it is quite friendly to a normal mechanic. Okay. And corrosion erosion resistant, because ejectors can be constructed from various materials which are not that costly, and a very high suction load at a reasonable vacuum. So, you can use it for filtration, drying, air conditioning and pumping of very large volumes of vapor. Of course, there are certain limitations. They need steam supply, and if there is a waste steam, definitely you should go for these things. Compared to liquid ring pumps, they generally require a bigger number of motorized valves because flow rate controls, etc., to operate properly. So, control is usually more complicated. Okay. So, when to use steam jet ejectors, when to use water ring pumps, when to use boosted water ring pumps, when to use backing of this water ring pump to the steam jet ejector, all that you have to decide depending on the vacuum level and the flow rate level. So, we have seen steam jet ejectors and water ring pumps now. So, later now we will go, their competitors recently coming last 20-30 years, they are in the same level of pressures, levels of vacuum, same flow rates, not very high flow rates, in the middle flow rates. They are comparable to these two pumps. They are called dry pumps like claw pump and screw pump. We will see in the next few classes. Thank you very much.